Question 24 then begins by asking us for an equation for the reaction of this acid RCOOH with sodium carbonate. When you have an organic acid like this, if you're not immediately comfortable writing the equation, it's quite helpful to think about what a simple acid would do. So if you just scribble down what the equation is for sodium carbonate reacting with, say, HCl, then basically the organic acid is going to do the same thing. So if you're comfortable writing this and you think, oh yeah, acid plus carbonate goes to salt, so that'll be 2 moles of NaCl plus water plus carbon dioxide. And then all you have to do is basically think, well, the organic acid is going to do the same thing. Sorry, we need 2 HCl to make that balance, of course. And the point is the balancing is going to be the same. So we just do the same thing and say, right, we need sodium carbonate. We'll need 2 moles of acid, so 2 moles of RCOOH. And we'll get 2 moles of the salt. And it gives you the formula of the salt. Organic salts are written slightly strangely so that the hydrogen here gets replaced with the metal ion, so RCOONA, plus water plus CO2. So you can see that approach, just thinking about what would a simple acid do and just modifying it very easily gives you the answer if you weren't quite sure how to do that one. Next then in part B it asks you to identify the concordant titers. Concordant means the ones that are close enough together that you think they're consistent with each other and should be averaged. And the rule that our exam board uses is that means you just take the ones that are most closely clustered together. So you have to look carefully, because what you can see here is we've got 27.2, we've got 27.25, so that's just 0.05 away from that one, but we've also got 27.3, which is 0.05 away from this one. So we've got this one, and this one, each separated by 0.05, but this one, 27.45, that's 0.1 away from, 0.15 away from the nearest other one. So that one is the one that gets left out. But we need to average all 3 of these. Okay, so it would be quite easy, for example, just to spot those 2 and not notice that one. So you've got to look carefully and see that you've got 3 equally spaced ones. So those are the ones that you go for. And so you get that the mean titer, and it's sort of fairly obvious what it is going to be the one in the middle, but we can write it out just to sort of justify what we're doing. 27.20 plus 27.25 plus 27.30 divided by 3, which is 27.25 cm cubed is our mean titer that we're going to use then in the calculation. Part C, now we come to the main bit of the mole calculation, which is to calculate how many moles of acid there were dissolved in the total 500 cm cubed, not just in the titration. So there's going to be a number of steps here, but the starting point in a titration calculation is always the same, that for one of the reactants you're going to know its concentration and you're going to know its volume, and you're going to use those numbers to get the moles that you need to get the calculation started. And in this case it's the sodium carbonate. So the first thing we work out is the moles of Na2CO3 in the titration. Okay, because that's always how we start. The one that we know the concentration of, we do moles equals concentration times volume in dm cubed. So when you've practiced enough titration calculations, that just becomes almost like a reflex response, that you know that's where you start. So the concentration was 0.05 moles per dm cubed, and the volume, now you've got to be careful, obviously there's a lot of volumes floating around here. The sodium carbonate was what you measured out with the pipette, right? So it said that you took a 25 cm cubed portion of sodium carbonate. So this is 25 cm cubed, is 0.025. It's not the burette volume, because that was the volume of acid, so you've got to watch out for that. So we've got to multiply those 2 numbers together, and that comes to 0.00125 moles. So then we come to our equation, which relates moles of this substance to moles of the other one, which is the one we're interested in, the acid. And so we get from the equation, and it's a good idea to write this down, partly because it makes your working clearer, but also because if you get in the habit of doing that, it'll prompt you to remember to check the equation, and it tells you that moles of RCOOH is double the moles of Na2CO3. Okay, so we've got to double that number, is 0.00250 moles in the titration. Okay, so that's not yet the answer to the question, because that's how many moles there were in the titration. Okay, but again, this is following the standard practice for titration calculations. You start off with the substance whose concentrations you know, figure out how many moles it is, then you look at the equation, use that to figure out how many moles of the other stuff. Now we come to the scaling up step, because that's how many moles there were in the titration, and in the titration our mean volume was 27.25 cm cubed. Okay, which we worked out a minute ago. So there's that many moles in 27.25 cm cubed. So now we've got to scale up and say, right, how many moles were there in 500 cm cubed? So that's the next step, that the total moles of RCOOH in 500 cm cubed, and it's just a scaling up operation. So if we multiply by 500 and divide by 27.25, we'll get the number we need, times 0.00250, which comes to 0.0459 moles. Now, if you're not clear why we did that, the way to think of it is to think, okay, we had 0.0025 moles in 27.25 cm cubed. So if we divide that number by 27.25, we get the number of moles in 1 cm cubed. Right, because you've got that number in 27.25, you divide that number by 27.25 and you get the number in 1 cm cubed, and then you multiply it by 500 to get the number in 500 cm cubed, and that's what that is in effect. So you can think of it that way if that helps. Divide by this volume to get the number of moles in 1 cm cubed, and multiply then by the total volume, which is 500. And that's just a way of making sure that you get this scaling up correct. So that's the answer for that part, the number of moles in 500 cm cubed. Next job now that we know how many moles of this we've got, we also of course know what mass of that we had, because it gave us that in the question. So we can combine those two to get the MR of that compound, and from that we can deduce what the formula needs to be. So we get that MR is equal to mass over moles, and we just plug in the numbers. So it told us that the mass that was dissolved in 500 cm cubed was 3.94 grams, and the moles in 500 is what we've just worked out, is 0.0459 moles, and if we do that calculation, that comes out to 85.9 is the MR. And that's the MR of RCOOH. So if we add up the MR of that bit, we can take that away in order to figure out what the MR of the R group is. So we get that COOH has an MR. If you add it up, we've got 12, 2 16ths and a 1, which adds up to 45.0, which means that the R group has an MR of 85.9 minus 45.0, which is 40.9. Now we know that R is just made out of carbon and hydrogens, which have whole number atomic masses, 1 for hydrogen, 12 for carbon, so that number needs to be rounded up to a whole number. So that's 41.0, and we do that because we can only get a whole number by adding up carbons and hydrogens. So we've got to work out how many carbons and hydrogens will give us an MR of 41. So to an extent you have to use trial and error here and say, well, how many carbons could it be? Well, if it was 4 carbons, that would add straight away 4 12s of 48, so that's too much. 3 carbons, 36, would leave 5 more, so that looks reasonable. 3 carbons, 5 hydrogens. If we had only 2 carbons, we'd need a huge number of hydrogens, so that doesn't work. So it's got to be, so that's consistent with, which really means it's got to be C3H5. Okay, because that has an MR of 41. Which means that the compound, because we've got to write out the proper formula, is C3H5COOH. C3H5, we know that if it was an alkyl group, in other words a saturated chain, it would be CnH2n plus 1 attached to whatever, in this case COOH, in which case we'd have C3H7COOH. So we know it's not a straightforward alkyl group. If you've got two fewer hydrogens, that means that it's either got an alkene group in it, which loses 2 hydrogens, or it's got a ring in it, which loses 2 hydrogens. And it could have been either one, except that it tells you in the question that it's an unsaturated carboxylic acid, meaning it has a double bond in it. So we know that that C3H5 group must contain an alkene group. And it also tells us that it's a cis stereoisomer. So if we think about what the possibilities are, C3H5 could be that with a COOH, but that can't have a cis isomer because it's got 2 hydrogens at this end. And if you have 2 groups the same attached to one of the carbons in the alkene group, you don't have cis transisomerism. So instead, it could be this. And that one does have EZ isomerism or cis transisomerism because we've got 2 different groups at this end and 2 different groups at that end. So we have to decide, is it this one or is it that one? Okay, so those are the 2 stereoisomers, just flipping the position of that methyl group at one end while keeping the other end the same. And we just have to know which end is cis. So remember, the rule is cis means that the 2 identical groups are on the same side. So we've got a hydrogen on this side and a hydrogen on this side, and so those 2 are on identical sides of the double bond, so that one is the cis one. Here you'd have a hydrogen here and a hydrogen there, so they are on opposite sides of the double bond, so that's the trans one. And so the answer is this one. So this, it asks us to write a skeletal formula out, so that means we've got to write the COOH group out in full. COOH, and that is our C3H5COH, and that's a cis unsaturated one which fits the requirement. And that's the end of the paper.